Your first job between now and the time you're done with your very last science class that's based on chemistry, so anything other than physics here, is to double check that any chemical equations that you have been presented are balanced before you begin working with them. This process involves counting the numbers of each type of atom on either side of the reaction arrow and ensuring that there are the same number of each type. Now, otherwise, your process violates the law of conservation of mass and the world ends. I'm kidding, the world obviously doesn't end, but anything you do with the equation is probably wrong since it wasn't balanced. So, to avoid either world's ending or you losing points on a quiz, which when you are a freshman is roughly the same thing, let's see what it means for an equation to be balanced. Now, in order to obey those fundamental laws that we saw in section 1.1, any chemical process will have to begin and end with the same number of each type of atom present. Now, let's say we want a reaction and go and find some molecules and a beaker. When we add those molecules to said beaker, the molecules can break down to atoms, and those atoms start to rearrange. What happens next is dictated in large part by the law of conservation of mass or matter, because our atoms will have to rearrange in such a way that none are lost and we don't gain any. There are options for what that next thing that happens actually is. This is largely going to be based on the identity of the reactants. Now, maybe our dissociated atoms like each other better than they like the other guy. So in that case, we will end with what we started with. Here, no reaction has occurred because nothing new was formed. But do notice that I have preserved the atom count. Maybe they like being atoms better than they like being molecules, and the process is just dissociation. 4 total atoms at the beginning, 4 total atoms at the end. Maybe all the atoms want to come together to make one larger molecule. Cool. 4 total atoms at the beginning, 4 total atoms at the end. Or maybe they just want to switch partners. Whatever happens will be based on what is reacting, and predicting which of these occur is outside the scope of this course, at least for reactants that look like this. The important take home from this slide is that in all cases, the total atom count is the same at the beginning and at the end of my process. 2 blue dots, 2 purple dots, each and every time. We'll eventually do calculations based on these balanced reactions, and if the atom count isn't correct before we start, our answers won't be correct when we're all done. We know what it means to be balanced, but how do we balance an equation that isn't already there? So let's pretend that the last subsection didn't have a whole video using this particular equation, and that we weren't sure if this is balanced or not. States of matter have been left off to keep the equation simple, but assume that everything here is in the gas phase. The first thing you would do is determine if there are the same number of each type of atom on both sides of the equation. Visually, my atom count looks something like this. There's not the same number of each type of atom, given by the different size colored circles on each side of that arrow. As this is written right now, matter has been destroyed, specifically 1 hydrogen atom and 1 fluorine atom, as they were present on the reactant side and they vanished somewhere before this reaction was complete. Since we have a law that states this can't actually be a thing, we need to work to ensure that there are the same number of circles on both sides of the reaction arrow. Now I can do that by doubling the number of each dot on the product side. Now the dots are even, so yay, but my equation isn't telling the same story as my dots do. To get the 2 stories straight, I need to indicate this action I just took in the balanced chemical equation. That indication comes in the form of changing the coefficient in front of the HF from the implied 1 to a 2 to tell the chemist that you needed 2 of that compound. Now voila, a balanced chemical equation. The practice video that comes later in the section does a few more complicated examples with 3 fairly specific tips. You'll definitely want to pay close attention and take careful notes on the tips it provides. But for now, we will do another with fairly simple chemical formulas. Here you've been given the names of compounds. Now we can't balance names, so we need to convert these to chemical formulas. There are a couple of places that you could trip up here. First, you have to be able to move from the name of an ionic compound to a chemical formula that represents the neutral species. So you had to remember the common charges on the monatomic ions and how to work with those charges in order to come up with NaCl. Second, you had to remember that chlorine was one of the 7 diatomic molecules. This means that in balanced equations, you will include a molecule of chlorine and not an atom of chlorine. That little subscript makes a big difference when balancing. The diatomic molecules trip up many students. You can be guaranteed they will show up on your quiz and midterm and final and 117. Continue to look out for your diatomic molecules. Anywho, all the warnings aside, now's the time to figure out how many of each type of atom there are across the arrow. If you're like me, you're not going to make pretty colored circles on scratch paper. You're more likely to scribble things down, perhaps in table form. A quick count from each side shows that our sodium atoms seem okay, but our chlorine atoms do not. So we have work to do. We need to double the chlorine atoms on the reactant side of the reaction. Keep in mind that we cannot change subscripts. NaCl2 does not exist. It isn't a neutral ionic compound. The only way to double the number of chlorine is to double the number of compounds that bring along that chlorine, which is the NaCl. We do so by adding a coefficient of 2 in front of its chemical formula. This action means that there are now 2 chlorines on each side, and those chlorines are balanced. But doubling the reactant chlorine also doubled the reactant sodium, and now those are unbalanced. Unbalancing a thing that was fine after balancing a thing that wasn't is going to happen all the time. It doesn't mean you did anything wrong. It means you need to keep going. Because if we double the number of product sodium atoms by adding a coefficient of 2 to that sodium, we'll be left with 2 sodium on both sides. The equation, this balances everything. Since the action didn't change the count of anything else, our whole equation is balanced at this point. I usually get asked if I have any tips for making balancing go faster, and the short answer is nothing more than what's included in the practice video that follows, which I know is not a popular answer. Balancing is really a matter of analyzing what you have, fixing one thing that looks fixable, reevaluating, fixing something else that looks fixable, if necessary, rinsing, repeating until you're done. There's a lot of back and forth. It does become easier with practice, but there's a lot of back and forth. Now, all that said, there's a series of steps that came from a textbook in the section page. OpenStax probably has a different, but mostly similar series of steps because it's all roughly the same. And you can definitely find other processes. The key will be for you to be consistent and do enough focused practice that you're comfortable handling anything that I can throw at you.